Okay, so let's actually go through these two examples of elimination, and so we can see how the process works. So remember that my goal with elimination as a strategy is just a different solution technique that you will find easier, especially when the given equations are already in standard form. Like if you tried to isolate either the x or the y, you would get something like y is equal to negative 2/5 x plus 3. That's just a little bit awkward to then substitute into the other equation where it's multiplying a 7. Yuck. So when they're already in standard form, maybe it's best that we try the elimination form. I conceive that if I multiplied the first equation through by 2, this would become a positive 4x. And that kind of matches with this one, a negative 4x. How does a positive 4x and a negative 4x cancel? Of course, by adding together. They would eliminate one another. So let's do this. We'll multiply the first equation through by 2, and it will become 4x plus 10y is equal to 30. Every term must be multiplied by 2. My second equation is still this. And now when I add the two equations together, I'm going to get these ones eliminating. 10y plus 7y is 17y. This gives me 17. Oh, that's lucky. Y is equal to 1. And then the process is exactly the same as it was for substitution. We'll substitute y equals 1 back into each of these equations, solve for x, and make sure we get the same thing. And so I'll just do that quickly without talking through it. Other equation. Oh, sorry, a bit of a wasted step there. Divide through by negative 4, and sorry, it's getting kind of cut off. So again, I get x equals 5. Same thing as I had in the first equation, and therefore we can conclude that I do have a solution of xy is equal to my x value is 5, and my y value I determined was 1. All right, second one. Elimination. So let's first begin by putting them into standard form, meaning that we move all the x's and y's over to the left-hand side, and all the constants, like the 11, over to the right-hand side. Now, you probably have an inkling about what's going to happen, but let's do the elimination technique anyway. And well, I've already got these ones matching up. That's nice. You remember that over here, they were opposites of one another, so we added the equations? Well, here, they're not opposites, they're the same. So let's subtract one from the other. So if I take the 6x minus y equals negative 7, and I subtract the equation 6x minus y equals negative 11, you know, it's probably more correct actually to write the second equation in parentheses, so that it's clear that when I'm subtracting the second equation, this subtraction is applying not only to the 6x, so 6x minus 6x is 0, they cancel, 0x, but the negative y minus a negative y, that's like saying a negative y plus a y. Well, they also cancel, don't they? Well, this also gives us 0y. They're gone, so 0. And negative 7 minus negative, so the plus 11, gives us 4. So what do I have on the left? I have 0 x's and 0 y's. What do I have? The answer isn't nothing. I have 0, which is a slightly different concept from nothing, which indicates possibly no number at all. Depends on the context, I suppose. 0 equals 4. And that is clearly an absurd statement. And so assuming that we've done the algebra correctly, there must be no values of x and y for which this equation can result, and therefore we've got no solutions. And if I've got no solutions, I don't have to worry about actually describing what they are. This shouldn't surprise us, because when I look at the two equations I formed from rearranging them, they became exactly the same. And if two equations, well, sorry, not exactly the same, maybe I should say a little bit differently then. If I isolated the y in both cases, I'd get 6x plus 7 in the first, 7, sorry, in the first equation, and I'd get 6x plus 11 in the second equation. Clearly the slopes are the same because the lines are parallel, and because my y-intercepts are different, they are never going to intersect, and I have 0 solutions. Last 2 examples, I think. Oh, no, I've got a few more. Well, I'll try to hurry. G. Again by elimination. This one's a little bit trickier to see. Maybe I should multiply the first one through by 3 to get 6x minus 9y equals 30. And then the second one, maybe I'll multiply through by 2 to get this. Okay. Now then, because the x's that I've manipulated to make sure they're equal to one another, or at least opposites of one another, they're opposite, so I want to add the second equation to the first equation. The 6x plus negative 6x, they cancel. Oh, but oh look, the negative 9y plus the positive 9y, those also cancel. So I've got 0 x's and 0 y's. And on the right, 30 plus negative 30, they cancel. What am I left with? 0 equals 0. This is true for all values x and y, so I have an infinitely many solutions, which implies that I've got coincident lines, that is to say lines right on top of each other, and I'm not really certain what the slope is, but I think it might look something a bit like this, let's say, and both lines are going to be right on top of one another because we do get identical equations. You might not see the identical equations at this stage. Certainly if I isolated the y in both cases and we looked at them in slope-intercept form, you would see that they're identical. Or perhaps you could argue that if we multiplied the second one through by negative 1, all the signs would change, and then you'd see that the standard form equations are the same. They must be the same line. And if we've got infinitely many solutions, let's describe the solution set as all values x, y, such that 2x minus 3y is equal to 10 is the rule that all of our solutions x, y have in common. Alright then, we've got a system of 3 equations this time. Let's use some elimination. A lot of you, I think, prefer maybe to add equations as opposed to subtracting, where you have to worry sometimes about subtracting negatives. So why don't we begin by adding together the first 2 equations here, such that the positive y and the negative y will cancel. So the x plus the x gives me a 2x, the z plus a 2z gives me 3z, and the 3 plus an 11 gives me 14. I also could eliminate the y in a different way if I looked at the second and third equations. So if I did x plus 2x, that would give me 3x. My y's eliminate because they cancel out if I'm adding, and 2z plus negative 1z gives me plus 1z. 11 plus 4 is 15. Now it is important to note that if you are going to use elimination in a system of 3 equations, you should endeavor to eliminate the same variable in both pairs. So if I use the first and the second equation, make sure I eliminate, and I'm eliminating the y, use a different pair of equations, but you must eliminate the same y. The reason we have to eliminate the same variable is that the 2 equations that we're left with, neither of them have got that variable, meaning that we've reduced the system of 3 equations into a system of 2 equations with only 2 unknowns. Let's continue and use elimination. Possibly I'd multiply the second equation through by 3, noticing that that now gives me a 3z in the first equation and a 3z in the second equation. Because the signs are the same, I should subtract. So I'll do 2x plus 3z equals 14. I'll subtract the equation 9x plus 3z equals 45. And that leaves me with, 2x minus 9x. The 3z's, of course, cancel. That's the whole point of my work. 14 minus 45 is negative 31. So looks like this is going to get ugly. I hope I haven't made a mistake somewhere. I didn't expect such ugly solutions. So x is going to be 31 over 7. Now we would bring our x back into one of these equations and figure out what z is. And then we would bring our x and our z back into any of the original equations and figure out what y is. So we'll substitute this x equals 31 over 7 into this first equation. I'll change my 14 into something with a denominator of 7. So that I've got, so 7 times 14 is 98. And I'm subtracting this 62 over 7 on this side. And that leaves me with 36 over 7. Such that z then must be 12 over 7. And now I'll substitute this x and this z back into one of the original equations, maybe the first one. 31 over 7 plus y plus z. And I'll change my 3 into a 21 over 7. And now I can in fact multiply the whole equation through by 7, giving me a 7y, and that will get rid of my fraction so I can solve for y. If I bring my 31 plus 12, that's 43, over to the right-hand side and subtract, 21 minus 43 is negative 22. So y is negative 22 over 7. Now, it would probably be a good idea at this stage to do a rigorous check of this x, y, and z in each of the three equations, but I would do that at the end of a quiz or a test when I've ensured that I've handled every question, just like I need to handle every example. So for the time being, I'm just going to write down my solution as 31 over 7, negative 22 over 7, and z is 12 over 7. Okay, and last example. So what are the value or values of k that satisfy the given condition for the system? If this system is consistent, that must mean that it is not inconsistent. Now remember that inconsistent. If it's not inconsistent, well then we should not have a situation where these two equations are identical. So let's manipulate, or try to manipulate, these equations so they're identical. How can we get the 2y looking exactly like a negative 9y? Well, we could multiply it by negative 4.5. So if we multiply this by negative 4.5, so I'm multiplying the first equation by this negative 4.5. So I got negative 4.5 kx, the 2 times negative 4.5 is negative 9y, and the 6 times negative 4.5 is negative 27. And so in my first equation, second equation is this. Well, I've managed to get my y's the same, and these ones are different, which is what I want in an inconsistent system, but if I want to have a consistent system, then I need to make sure that these ones are, well, let me just think about what I want to do here. If it's not inconsistent, it must be consistent. The two choices then are consistent independent, which would mean that these values are different. So the coefficients can't be the same. And that must mean that k cannot equal 4 over negative 4.5 before I double it. K cannot equal negative 8 over 9, or that would give me a consistent dependent system. Can I ever have a consistent independent system? Can I have a consistent dependent system? Well, no, because these ones can never be identical. So as long as k is not equal to negative 8 over 9, then I am not inconsistent. In the second one, how can I make sure it is inconsistent? If it is inconsistent, that must mean that once the variables have been lined up, I've got different values here. So let's multiply the first equation by 3.5, and that gives me 7x plus 10.5y, and negative 4 gives me negative 14 times 3.5. Whoops, yeah, that's right. And so now my x's are the same, and now these guys are the same. Oh, well, I mean, obviously my y coefficients would have to be the same, so negative k would have to equal 10.5, so k has to equal negative 10.5, but my right-hand sides are the same. So the only value k can equal when my x values are the same is negative 10.5, but that means that my entire equations are the same, and that would mean that it's a consistent dependent system. So there is no solution for this example. Okay, k has no solution.